time, the excited wavelength still equal to the E1 minus E2. Here you have n equal to its own quantum number. So when here you have n, here, so you have n equal to 1, that means the ground state. You move to n2, so that means 1 excitation, and 3, and 4, 5, and 6, and so on. So X moving like this, is electron transition like this, corresponding with a different energy transition. And if the electron go to very far from the nuclei, that means you remove the electron from the atom. So in that case, you have ionized state. That means you remove completely electron from the atomic structure. Okay. So what we can learn from the Bohr model? We can say that Bohr model is quite simple, easy to understand, but it have a great success to explain the case of hydrogen atom. But when we try to apply Bohr model to other atom, more than one electron, we have a difficulty. The difficulty comes to the fact that we cannot explain the emission spectrum of other atoms like sodium. So people need to improve the Bohr model again. However, from the Bohr model, we can retain two important useful ideas. Electrons in the atom have only certain discrete energy level. Electron cannot stand everywhere, and we have all full spectrum of the potential energy. They have only certain discrete energy level. Energy is exchanged in moving an electron from one level to another, one allowed level to another allowed level. Okay, there are two main useful ideas for the moment. Then, after Bohr model, there's at that time there were a revolution in the quantum physics, in the physics. So people come back to the Bohr model and figure out several difficulties. Like say, Bohr could not explain why electrons were restricted to some fixed distance around the nuclei. Bohr assumed that electron can stand only in several discrete radii, so corresponding with different discrete energy level. But he cannot. That's poor an assumption. He cannot explain why. So at that time, Louis de Broglie proposed that if light can behave as a particle, photon, then particle can exhibit also the wave characteristics. It's something seem quite confusing, but important. Let's say light is a wave, a magnetic wave, behave like particle. So we can also imagine that particle in moving can behave at a light, at a wave. Okay? And remember that's why Louis de Broglie mentioned about this, because we remember electron is a pointless particle, no dimension. So if electron move at a particle, then we can imagine also electron can behave like a wave. Okay, so that's the main idea proposed by Louis de Broglie. So what I mean, particle movement can emit the wave. So that means if a particle stands, then nothing happens. But if it's moving, then it's going to emit associates with a photon release with a wave, right? So that's so he proposed an equation lambda equal to S over mu, where you have lambda is the wavelength associated to the particle when the particle have the mass and moving with the velocity u. Okay, so by using this equation, imagine that if you take one electron moving at the rate of 10 power 6 meters per second, this electron will have associated wave of 10 minus 10 meters. So it's about 0.1 nanometer. It's very small, so that cannot detect earlier. Okay. Now, a little bit challenging for you. If you take this idea and try to calculate the wavelength associated to your movement, what could be the wavelength of this associated wave? Let's say, take a joke, huh? People say that this guy is very talented, he shine like a star, right? So you say whether it's have a physical meaning. Một ai đấy tỏa sáng. Is this correct? Can we observe this guy wavelength associated with him? So if you take this guy funny calculation, you pick up one guy, he can run 100 meters in 10 seconds. It's about the best world record now. So that means the velocity is equal to 10 meters per second. And assume that this guy have the mass equal to 80 kg. So now you can calculate the lambda equal to 6 power 6, 34 kg. Yes, you have 80, 10 kg m over s. So you can remove this one, you can remove this one, you can remove this, and it becomes m1. So it's equal to 6.6, 10 minus 34 over 800 met. So it will be approximately of 830 minus 35 met. So it is when equal to 8 nanometer. See, so it's extremely small. We cannot detect this guy of wavelength. So someone say this guy he's sailing like star is just how to say literature saying. It's not really physical meaning. Okay. So with the evolution of quantum mechanics, the quantum physics, we accept the idea that electron is a particle, and because the electron moving around the nuclei, so it's behave like a wave. Okay, that's the more important. So here you have few main features of quantum mechanics. The wave cannot be precisely localized. Okay, and as electron behave like a wave, so the electron cannot be precisely localized. Is on the point to rule out the proposition made by Bohr. because Bohr say that, Bohr assume that if you have a nuclei, and the electron will move around the nuclei in different orbit like this. Okay. If it's then, you know precisely the position of electron. But here, because electron behave like wave, they cannot be precisely localized. So you don't know exactly the position of this one. Okay. More exactly, we cannot know at the same time the speed and position of electron. It means if you know the speed of movement of electron, you don't know energy. You don't know the position. If you know the position, you don't know the speed. It means if you know the position, you don't know energy, and if you know energy, you don't know position. Okay. So to overcome this one, they are described by the wave function. We give the probability of presence in some portion of space and energy. So now we don't talk anymore about the precise position of electron, but we will say the probability, the chance to find electron in a given space. It gets more complicated now. So to solve the probability to find the electron in space, you need to solve the Schrodinger equation. Just to fighting you a little bit. We will not need to solve this equation for the moment. What we can learn from this is that because electron behave like a wave, so we will use a wave function to describe the probability to give the probability to find electron in a space. So you can imagine that now we need to know in one given space around the nuclei, what could be the probability to find electron? Not exactly 100% that I can find electron here, but what could be the probability? So by solving this wave function, you can see the electron density in a volume in a space around the nuclei. So for example, by putting the result of wave function on a diagram of XYZ diagram like this, you pick up the position of the nuclei. You can see the density of electrons around the nuclei. So you say that the probability to find electron is very high in this space. When you go further in this position, you still have probability to find electron, but it's going to be lower. Okay? So we can say that the density of electron or the probability to find electron surround nuclei, it depends on the nature of the electron and of course the nature of the nuclei as well. Okay. So now with this idea, we go to the atomic orbital. The wave function as stellar wave around the nuclei. So the solution of Schrodinger equation for the hydrogen atom is a set of wave function and corresponding energy. There's a lower energy station wave and higher energy one. the lowest energy one, we call the growth state. The wave function are called orbital. So you see that there's difference between orbit using by Bohr, and here you have orbital. Orbit, say you have nuclei, and what could be the precise circle, if you want, where you can find exactly the position of electron. The orbital, say you have nuclei, and you have a space, you have a portion of space where you have a high probability, you have a high chance to find electron. So it's not exact, the circle like this, but the orbital means the space where you have high probability to find electron. That's the main concept of the orbital. Okay. So X orbital describes a specific distribution of electron density in space. Okay. And X orbital have a characteristic energy and state. X orbital in an atom is characterized by a unique set of 3 quantum number. From the Schrödinger wave equation, you have 3 quantum number and the main quantum number L and ML. Now we go a little bit more detail what they are. So the first quantum number N is principal quantum number, has positive integral value. It's always 1, 2, 3, and so on. If the value of N increase, the orbital become larger, and the electron spend more time far from the nuclei. The smaller N, that means the electron gets closer to the nuclei, and higher value of N, that means the electron get farther from the nuclei. The electron have higher energy when the value of N increase. That means also the bonding energy with nuclei get decreased. The electron is less tight bound with nuclei, right? So it also means it can easily be removed from the atom if it migrate at the higher value N. You have the second quantum number, which is L, angular momentum quantum number. It has integral value and range from 0 to N minus 1 for each value of N. So for example, if you have an N equal to 1, then L have only one unique value, 0. If you have an N equal to 3, you can have L equal to 0, 1, or 2, because 2 equal to 3 minus 1. The angular momentum quantum number, L, defines the shape of the orbital. And they are named by the letter S, D, D, F, depending on the value of L. For example, if you have 0, the orbital name is S, 1 is P, 2, D, and 3, F. And because it decides the shape of the orbital, so when you have S orbital and P orbital, the shape will be not the same. ML is magnetic quantum number, describe the orientation of the orbital in the space, and have integral value between minus L and L, including the 0. For example, if you have L equal to 1, that means the orbital P, so you will have ML equal to minus 1, 0, and 1. So that means the orbital B can have 3 orientation different. If you have L equal to 0, that means orbital S, you have ML equal to 0. So that means the orbital S have only one orientation. You will have the shape later. Okay, so how can we manage the quantum number? So the value main quantum number is integer number, different than 0. L equal L can get integer number from 0 to n minus 1. ML can be minus L, including 0 up to plus L. So let's say if you have main quantum number L equal to 1, L will have only value for 0. And if L equal to 0, so ML equal to 0, so you have just only one orbital with the set of 3 quantum number 1, 0, 0. This is orbital 1s, because 1 comes from n equal to 1, and s because L equal to 0. You do the same thing for the L equal to 2, you have two value, L equal to 0 and 1. For 0, you have one orbital 2, 0, 0, so you have orbital 2s, because n equal to 2 and L equal to 0, so that's it, orbital s. The same thing for L equal to 1, you have ML minus 1, 0, and 1, so you have 3 orbital with a 3 set of quantum number 2, 1, minus 1, 2, 1, 0, 2, 1, 1. So this orbital is orbital 2p, because you have n equal to 2 and p because L equal to 1. So that's the way you manage the 3 quantum number to describe the x orbital. Okay. So here, this table summarize give you a summary of how you manage the quantum number. So orbital have orbital energy level in hydrogen atom. You can see here in the diagram, and you can say that x orbital is defined by a set of 3 quantum number, but the energy of orbital depends only on the value of n. Okay, so all orbital in one cell have the same energy. So let's say if you have orbital 2s and 2p, they are in the same cell, so they have the same energy. So here you see that you put in the same level of energy. N equal to 1, of course, you have only 1s, so there are no question. In the case of the third layer or third cell, you have a 3 orbital, 3s, 3p, and 3d. Because the energy level depends only on the value of n, so we say that the 3 orbital have the same energy level. Okay. So now we look a little bit about the representation of the orbital. First, we talk orbital is the probability of finding electron in the space surround the nuclei. So now we look a function giving the probability to find electron in function of the distance from the nuclei. So you can see here in the orbital 1s, in the x, if you take the nuclei here, okay, you see that in the distance very close to the nuclei, very close to 0, the probability to find electron is low. The highest probability to find electron is here. Okay, so you can say the orbital 1s is something like this. So the highest probability to find electron surround the nuclei in 1s is about 1 angstrom. Doing the same thing for the 2s, you can see that the highest probability to find electron is here. So you can represent, if you want, the orbital 2s like this one. Huh? And 3s also like this. It must become much bigger. What is interesting thing is that even for the case of 2s, you can find also the probability to find electron very close to the nuclei. Even most of the time, you have a higher probability to find electron far from the nuclei. So you can say, in general, you can say the orbital 2s is bigger, have a bigger size than 1s, and a smaller size than 3s orbital. But it doesn't mean you would not find electron near to the nuclei for the orbital 3s and 2s. It's important because later when you do the calculation of effective charge of the nuclei on the electron, you see that you have an electron in the third layer, but electron in the third layer, 3s, can also migrate near to the nuclei. So in the case, it goes near to the nuclei, it will mask the interaction of nuclei with the outermost layer of electron. Okay, so we will be back later. But for the moment, keep take-home message is that orbital 2s have a bigger size than 1s and smaller size than 3s. But we can have also the probability to find electron 2s close to the nuclei at the distance of 1s. That means the electron in orbital 2s can jump, can find some probability near to the nuclei as well. That's it, right? So you can see here, 1s smaller than 2s and 3s. S have a spherical shape because it have only one unique orientation. And we say that the orbital representing the volume of the space, the portion of space around the surround the nuclei, where you can find a high where you can have high probability to find electron. But what does it mean, high probability? High probability can be 80%, 90%, 95%, but never 100%. Because if you can find it's 100%, that means you can know exactly the position of electron, which is not the case for the mechanical quantum mechanics. If you can find exactly precisely the position of electron, that means you are back in the assumption made by Bohr when he say that the electron runs around the nuclei in the orbit, not orbital. Okay. So okay, now we talk about the shape of the orbital. You know that in previous slide we mentioned that the orbital S is spherical shape, and in the case of orbital P, you have dumbbell shape, as you see here, and you know that it have three value ml equal to -1, 0, and 1. So that means you have three different orientation in the space. So you can see here, if you take the coordinates x, y, z, you can have three different orientation: one z, bz, bx, and by, like this one. Okay. How about the orbital d? So orbital d, you have 5 different orientation. So you have d, y, z, xz, xy, x power 2 minus y power 2, and dz power 2. Okay, so that's for orbital d. And orbital d, we start to have is on the third layer. So we start from the 3D. Now imagine that you put all of the phi orbital d, phi orbital d in the same coordinate like this. And imagine that you have a compound which have the M here, and you have one molecule water here, and one molecule water here, one molecule water here, and one molecule water here. So it looks like you have this set. Clone the octahedral. Let's say M is to 6. 1, 2, 3, 4, 5, 6. What will happen? You will see that for the first molecule, water here, is have a direct interaction with the d orbital h power 2 minus y power 2. And for this molecule water on the z, you will have the direct interaction with the orbital dz square. So that means if you take 6 molecule of water, they will have a direct, we can say, or close interaction with dx minus y minus and dz square. Okay? How about this orbital? Let's say this one. Let's talk about this one. The xy, right? So the molecule water stand here and here, here, and here. So it looks like you have a molecule water and the orbital is in between the two molecule water. So we can say that the dxy has phi interaction or weak interaction with water molecule. Can you see it? Because the orbital dxy stand in between this plane. So the molecule water here, they stand on x and y, and the molecule the orbital dxy is in between like this. So the distance from the d orbital and the molecule water stand here is quite far. So you can say that the same thing for dxz and dyz. So basically, if you take this molecule with the metal M, so have the d orbital, and 6 molecule water arranged in the octahedral geometry, you can see that phi d orbital will not have the same interaction with 6 molecule water. It will have 2 set of orbital, dx, y, dz, have a strong interaction. And you have a second set of orbital, xy, d, have weak interaction. You see, before we say that, the energy of orbital depend on the main quantum number n. It say normally phi orbital d will have the same energy level. Is it correct? However, if you put phi orbital d in the interaction with 6 molecule water arranged in x, y, z in the octahedral as I described here, the phi orbital d are no longer having identical energy. They will split in two groups with two different energy levels. Till now, do you understand? Hello. Is it okay?
Kinda.
Okay. I think
You understand, right?
I think
Okay.
any
So now, why I explain this? Because it's important. When you say the energy of orbital depends only on the main quantum number, is when only the atoms stand alone without the interaction with the environment. Here I put an example, a demonstration to say that when you put one atom, whatever the metal M here, M represents for metal, which have 5 orbital d. Normally, by definition, if the M stand alone, the 5 orbital d will be similar, will have a similar energy level. They are identical. However, when the atom M interact with 6 molecule water, and 6 molecule water arranged in the geometry with the octahedral I draw here, then the 5D orbital are no longer identical in terms of energy, because the distance and the interaction with the molecule water are not identical. You will have two groups of orbital d. One have a strong and short distance and strong interaction with 6 molecule water, which are orbital d x square minus y square and dy z square. And the second set of 3 orbital dxy, dyz, dxz. They are now they are splitting into energy level. Why I mentioned about this? First, to tell you that all what we learn now, considering isolated system, that means the atom will not have interaction with environment, which is not the case for the chemistry, for the chemical reaction, because we will rarely have something standalone. We need to consider about the environment, so first thing. So try to understand that's what we learn is the ideal case, and the reality, what we observe is a little bit different. The second thing, with this splitting of energy, we can explain several interesting phenomena. For example, following, I show you the following experiment. Okay, this one. This is experimentally what we can observe in the lab. Let's say if you take the dry cobalt nitrate, this one. If you take the example, cobalt nitrate, the dry one have no color, colorless powder. But if you put this compound in water, it will have pink solution. Does that mean you can start to observe the color? And then if you drop Na3 into this solution, you change the color from pink to the blue solution. Can we explain this phenomenon? Anyone can try to explain. How can we explain this phenomenon? the color change can change from dry compound to the wetting compound, and when it drop water ammonia inside the color change. How can we explain it? Hmm? Anyone? How can we explain this phenomenon? First, why this compound has no color? Các bạn có đang nghĩ không đây? Hmm?
Bọn em đang cố ạ.
Same.
Trí, tính trí.
Okay, so the light is the product of photon absorption and emission. So for CO carbon nitrate, the wave that associate with the emission is not in the I forgot the term.
Okay.
We can't observe the photon, so it's colorless. For water
But
molecule.
Okay, Chi, sorry, but why it cannot absorb photon?
It absorbs photon, but the wave that associate with it, we cannot see with their eyes. So it's colorless.
So what the photon absorbed by this compound? What could be the wavelength of the photon absorbed by this compound?
The wavelength. It can't be observed by normal eyes, so it's colorless.
Okay, let's move on. So then, why the cobalt with water can become a pink color?
As you said before, the H2O will interact with the cobalt. Specifically interact with the d orbitals of the cobalt. So it will split the d orbital into two states of energy. And the difference in that energy is associated with a wavelength that we can observe with our eyes.
Okay. Then
I believe the term is visible region.
Okay, and then why when you drop an H3 inside, it become blue color?
The effect of ammonia and water to the D orbital is different, so you will get different colors.
Okay. We still have time, but I think that's because we will continue our lecture. We will discuss. We already discussed about the electronic structure for the moment for only one electron till now, one electron system. In the next section, we will talk about the multi-electron system. Sorry, multi-electron system. So I propose here because I propose we discuss about this question because it's so the degeneration of orbital D depend on the environment, depend on water, energy, and so on, and how it's linked with the color of the compound that we observe. So may I propose that we end our lecture here today here, and I invite you guys all to try to answer this question at home, and then when we will discuss in the next section about this question before we move for the multi-electron system. Do you agree with us?
Okay, sir.
Okay, so it's quite important trying to apply what you learn, very general thing, to solve some phenomena that we observe in the lab and that we observe in our life. Okay, so try to solve question. First, answer question. Why we see the color? What could be the relationship between the wavelength the compound absorb and the color we see of the compound? Okay, why one compound have blue color, another one have a pink color? Because of the absorption difference, but how the absorption wavelength of the compound is associated with the color that we see of the compound. First question. Second, answer the question why the dry cobalt nitrates have no color, whether it's absorbed, but it's absorbed in the wavelength that we cannot see, or it doesn't absorb anything. In what case, in which circumstance one compound will absorb, and in which circumstance the absorption is not happen. And then second, why when you add water inside, you see the pink color? Because it's absorbed in which kind of wavelength. And when you move to Na3, you drop Na3 inside, you see the color change because the absorption change. But why that the absorption change? And in terms of energy, how the energy splitting of the orbital D change when you change from water to ammonia? Is it okay? So those are the several questions. I wish you guys, I invite you guys work at home, discuss each other, and we will be back to this question next section before we move to complete our lecture on the multi-electron system. Okay?
Okay, sir.
Okay, teacher.
Okay, thank you guys.